This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, let's welcome back to our next part of our lecture. I think we're going to do polymer viscosity, and then we might just do emulsions. Probably the whole thing will be about an hour and a half, and we'll just finish it in two parts. So viscosity of polymer solutions. Polymers, polysaccharides, carboxymethylcellulose, guar gums, polyacrylates, are very commonly used as viscosity control and thickening agents in products. You'll see them in cosmetics, pharmaceuticals, foods, mining products. So they are really useful in modifying viscosity. And basically they're able to do that because of how they change shape in solution, and also how they interact with each other and the solvents. So whether or not it's in a theta solvent or a good solvent or a bad solvent can matter, but also how the polymers interact with each other can matter as well. And so that's what we're kind of going to start to explore today. We're going to start with viscosity of polymers. Similar concepts apply for rheology next week in terms of the behavior you see, and we'll really get more in rheology. We're going to try to limit this to simple Newtonian viscosity or talk about the dilute aspects of polymers today as a warm-up for some of the same concepts we'll see in emulsions, and then we'll really get into non-Newtonian fluids next week. So if I think about a polymer, its characteristics that are relevant for viscosity and flow are going to be molecular weight, its end-to-end distance. You can think of it as its radius of gyration, its Flory radius, or literally just its radius of end-to-end distance. And that's reflective of its end-to-end distance when it's a dilute polymer is its radius of gyration. But when it has a lot of nearest neighbors, it gets somewhat compressed. And also the chain expansion factor, which is again just getting back to the solvent quality. So the way to talk about viscosity, and I'm so sorry, I actually cleaned this up on the next slide, so we'll just ignore this part because I cleaned it up on the next slide. So you can talk about the viscosity of a dilute solution can be used what's using an Einstein relationship. So Einstein had figured out that the viscosity of a solution increases when you take a solvent, which is what NS stands for, is viscosity of a solvent, and this is the viscosity of the whole mixture, eta. And so eta S is the solvent. And if you add things into a solvent, and you effectively add spheres into a solvent, the volume fraction of those spheres, which is what phi is, it's just its volume fraction, is that there's a very simple relationship for small volume fractions, well below 10%, maybe 5%. It says that, you know what, the viscosity of the solvent, if you add some things that are spheres, now you might think of spheres as particles. If you added spherical particles into solution and their volume fraction, the amount of water they displaced might be, I don't know, 1%, you could actually predict how the viscosity of the mixture should go up if you know the solvent and just the volume fraction of the spheres. In fact, you don't even need to know the size of them. You can just know their volume fraction and get a reasonable prediction of how the viscosity of that solution might go up. And this is if you're adding so few spheres, they're not really interacting strongly with each other. Now, with a little bit of math, we might define that a little differently for that relationship, where we've just multiplied things out. And I've created a different term where I've got viscosity minus the solvent viscosity divided by the solvent viscosity. So you could think of that as like a normalized change. How much does the mixture increase as a percentage off the solvent? So how much more viscous is it than the solvent? And then it's just 2.5 times the volume fraction of spheres I've added. Now for a polymer, I can approximate a polymer as a sphere where I can figure out, well, what's the N over V is just going to be the number of molecules per unit volume. So that would be the number of polymer molecules. And then I say, well, then if I say the number of polymer molecules times the volume of a sphere, that'll give me my volume fraction. So that's another way to just do a little bit of algebra substitution to start to say, well, the number of spheres times the volume of the spheres gives me the volume fraction. And so the reason why I do that is I'm going to, in the first instance, approximate a polymer as having a volume of a sphere. And in dilute solutions, remember with a radius of gyration, that's not outlandish. Now, the reason I do that is it lets me get a little bit further in describing viscosity, and I'm just going to take you through this derivation to define some of viscosity terms. It's going to seem peculiar, but at the end of the rainbow, why we're doing this is we're deriving a formula that shows you how we might characterize viscosity of a polymer, and then what we might do if we can measure the viscosity of a solution. And it's the warm-up. It's the first time we've really started talking about viscosity. So all I've done is just I put that up here as saying, okay, well, I can describe this kind of relative viscosity as the number of molecules times the volume of the sphere. Well, I can say, well, the number of molecules divided by the volume of the sphere can also be the concentration times Avogadro's number, because that's another way to get number of divided by its molecular weight. That also gives me the number of molecules per volume. And so that's the number that where C is the concentration, M is the molecular weight. And so I can replace that. And why I bother is, well, these are quantities I'm much more likely to know. I might know the molecular weight of the polymer. I ideally would know its concentration, and I know it's Avogadro's number. So I'm actually getting down to seeing how the viscosity might depend on molecular weight, which somehow seems like something I should start to understand for polymers. I still have the volume of a sphere. Now, if I say a volume of a sphere is for a random coil, you can actually say it's proportional to the cube of the root mean square end-to-end distance. And you can have to take that as a difference, kind of a given. But it's basically saying the average distance is the root mean square of the cube root of the root mean square of a polymer. And so you're basically saying there's an average distance of a polymer from its end to end. You're kind of equating that to a radius and saying, well, then that polymer, as it moves around and its kind of average radius carves out a sphere. You can see there's an alpha in there again, and that alpha is just accounting for solvent quality. It's called a hydrodynamic chain dimension because it's in viscosity form, but it's basically just saying, well, there's the size of the random coil, and then I'll have a fudge factor to say whether or not it's in a good or bad solvent. But I can describe the volume that that polymer carves out in terms of actually something that's related to the dimensions of the polymer. And so I'm going to substitute in that into here. Well, I could substitute it in at that point, sorry, but I'm going to push it a little further. I've defined that volume. I'll come back to it. It's easier to do the derivation without it. So I've got another viscosity. So the specific viscosity is actually this one I've been referring to. So it's the difference in the viscosity from the solvent divided by the solvent's viscosity. So that's kind of a percent increase. How much more viscous is the polymer solution because it has a polymer in it. Now, I want to talk about, and so that's actually probably, I mean, this is a useful thing because this might be a quantity I could measure the left-hand side. I might throw concentration on that side. That's something I could measure. But if I want to describe the intrinsic viscosity of a polymer, why is a polymer viscous? I actually need to talk about the specific viscosity as the limit of infinite dilution, where basically the polymer causes the solvent to be a higher viscosity just because the polymer's in it, not because it's bumping into other polymers. And so I'm going to define yet another viscosity called the intrinsic viscosity. So I've got the viscosity of the mixture, eta. I've got the viscosity of the solvent, eta S. I've got the specific viscosity, the viscosity of, it's kind of a normalized increase in the viscosity of the mixture with respect to the solvent. And then I can have the intrinsic viscosity, which is the viscosity intrinsic to a polymer as if it was a polymer on its own and didn't see any other polymers. And so that's taking the specific viscosity divided by concentration as the limit of concentration goes to 0. And no, that's not supposed to be obvious why that's there. That's because a lot of people spend a lot of time looking at polymer solution theory. So what happens though is if I take the intrinsic viscosity, which is effectively this, because what's happened is the concentration's dropped out of it because it's gone to 0. When I took that, I divided by concentration and took the limit to 0. Now I'm going to plug the sphere in. And what I'm going to combine to is that I take the limit of the specific viscosity times concentration. On the bottom, as it goes to 0, I get the intrinsic viscosity, which is Avogadro's number, molecular weight, and expansion factor, and basically the size of the polymer. Now, a lot of these things are constants, and they can get lumped into this kind of lump. I mean, alpha is going to be a constant, Na is going to be a constant, 2.5 is going to be a constant. And this is what's called the Flory-Fox equation, where this is a constant that has a generic number to it. But after all this, what I can see is the intrinsic viscosity, how much the viscosity changes the solvent viscosity, even though it's not even interacting with another polymer. It's intrinsically, the viscosity goes up by the square root of the molecular weight. And that's what happens when I do a little bit of math. And so, and by the way, that's not meant to be obvious, because you'll see the R comes out of there and the R gets related back to molecular weight. And you're welcome to look up the derivation of this, but I don't really care about you knowing the derivation of this. I might like you to know specific viscosity and this form of viscosity, but that's for measurement. What happens is, if you generalize this to any polymer, you make the Mark-Howink relation, which basically says the intrinsic viscosity for any polymer solvent temperature combination it's kind of a material property of that particular system. So it's its molecular weight raised to a power times K. And these are tabulated for polyethylene and Decalin at a particular temperature. You can look up its K and its molecular weight. Now, what these things are telling you is the constant A varies between 0.5 to 0.8. K, on the other hand, is effectively a guide for, if you put this polymer in infinite dilution in that solvent, it'll tell you kind of the conformation of it. So if it's a hard sphere, it's a bad solvent. If it's a random coil, K is 0.5 to 1. And if it's 1.8, it's a rigid rod. And anything between 1 and 1.8 is becoming a rigid rod. So very quickly, the Mark-Howink relationship can tell me a couple things. I can look up polymers and say, hey, if I put it in the solvent, is it going to be a good solvent, a bad solvent? Is it going to be like a hard sphere? I can just look at the K value. Is it going to be a random coil, or is it going to be a rigid rod? And I might care about that in terms of how the polymer behaves in a particular solvent. And sometimes I might be using this because I know I need the solvent to be a random coil, because that's what I'm looking for in terms of its properties and how it's going to interact with the rest of the formulation. And I might be going, well, what polymer with what solvent at the temperature I'm going to be working at? Well, tell me about that geometry. So that's one thing it's useful for. But the other thing this is useful for is, this is effectively a material property of a polymer. And it's measured it's basically measured off calibration standards, where you basically measure the intrinsic viscosity for the same polymer of different molecular weights, and there's regressions you can do to measure this. And so people have measured this. It's kind of like a thermodynamic, a material property you would use. But the Mark-Howink relations, those K and A parameters, along with intrinsic viscosity, can then be used to take a polymer solution where you don't know the molecular weight. Maybe you have a polymer solution at a couple different concentrations. This is actually the relationship and data that's used to determine the molecular weight measurement of a polymer. And so this, of course, is treating polymers as isolated and penetrable hard spheres. This is still in the dilute region. There is a non-dilute scenario where polymers start to entangle, and the viscosity gets much more complicated. We'll come back to this in a minute. But while we're talking about dilute systems, what do I mean by how is this used? So typically, for any particular polymer solvent combination, which is what you saw here, there's a polymer solvent combination, I might have a sample of polymer. Now, a lot of polymers are many molecular weights, and their molecular weight could be different, their molecular weight can vary, or I'm trying to figure out what molecular weight I need to get a particular viscosity. And molecular weight affects viscosity, but so does the concentration of the polymer in solution. And so people will make measurements where they take the concentration and multiply it by the intrinsic viscosity, and then you have this relationship up here where you measure the viscosity of the mixture and the solvent, and you take the and you also calculate that with the intrinsic viscosity. And what you can get from that is you can actually go back and determine the molecular weight of the polymer solution you're working with. And how this works is well, this is one example. There's a number of correlations. We'll just use the Martin equation, where the viscosity is the solvent viscosity, where it's defined as this series, where it's 1 plus the intrinsic viscosity times concentration, then the intrinsic viscosity squared times concentration. And if you play around with the infinite series, what you can find is that this is effectively the specific viscosity over concentration, right? That's what that is on the left. The specific viscosity over concentration can be related to the Howick relationship, concentration, the intrinsic viscosity twice, and there's a K in there. But what that means is if you measure the specific viscosity divided by concentration and plot that versus on a log scale and plot it versus concentration, you can effectively determine the intrinsic viscosity. And if you can determine the intrinsic viscosity, you already know what K and A are, so you can determine the molecular weight. And how these viscosities of the mixtures are measured are very commonly with glass viscometers, and I'll get to those in a second. But this can be used to measure molecular weight, and that's kind of why I dragged you through this. This is what you would do to understand polymer solution viscosity if it was in a dilute system. If it wasn't in a dilute system, it'd be much more complicated, and that's what non-Newtonian rheology is. These pictures over here are viscometers. There's an Ublahold type and a Cannon-Fensky type. And basically, they're very carefully machined glass tubes. They're often in temperature baths, and they're designed to have liquid in them that you normally use a bulb to push the liquid up and then time how long it takes to go from one part to the other. And so this one will push the liquid up and then time how long it takes for it to go back down. And by timing how long it takes for the liquid to go between those two points, you know very accurately what the volumes and the diameters are, and there's an equation normally that will let you calculate the viscosity of that mixture. And so by measuring the viscosity of a polymer solution, you can actually figure out its molecular weight. And there's lots of other characterization methods that you'll hear about after the week after next, where you can use it to measure viscosity of materials. But this is kind of a very basic way to go about doing it, particularly for dilute solutions, where the viscosity is higher than the solvent, but the viscosity is still a constant for a particular concentration. So, of course, that's what a Newtonian fluid is, where the viscosity is constant regardless of how quickly you're flowing it or its shear rate. A non-Newtonian fluid means the viscosity changes depending on how quickly the flow rate is or how quickly the material is being deformed. Now, in dilute solutions, there's kind of basic polymer viscosity. That was kind of an advertisement for it. But that's assuming basically the polymers aren't bumping into each other. And so I've got this schematic, which is not terribly beautifully written, but that's kind of on purpose. But you could think of each polymer's kind of got a mean coil size around it. And when they're infinite dilution, basically the coils are defined, their size is defined by the radius of gyration, and they're not really bumping into each other. But as you increase the polymer concentration, and now we're starting to get to a region where this is what we've looked at so far. This is, infinite dilution. But when you start to get to where the coils overlap, then first they bump into each other, and this is their overlap concentration. Now, they're bumping into each other, but their size really isn't changing. They're still the same size, but now they're actually bumping into each other. So if you try to flow or measure viscosity, those polymers are going to slide over each other. Then you actually, as you start to increase the concentration, the polymers actually, the coils themselves get a little smaller because they start to contract. This is kind of analogous to on a brush when they would contract as well. And so the coils contract. And then you get to an additional concentration where they can't squish anymore. And so if you add more material in there, you're just getting rid of solvent and moving it towards a polymer melt. And what you've got is each concentration effect has a different regime. And so what happens is as the concentration goes up, this might be more like the radius of gyration, and that C star as they start to bump into each other, and then they start to contract, and then they really can't get any smaller. and they're kind of at their either they're at almost their melt state, and so the polymers themselves get crowded and they get squished together. Now I've got one more slide, and then I'm going to ask why would I care about this. So in the dilute region, what defines when these two when you're in one region or another? When are you in the dilute region? When are they starting to bump into each other? When are they starting to entangle? Depends on the concentration and the molecular weight. The higher the molecular weight, the more likely they are to entangle, and the higher the concentration. So there's a large region where they're very dilute, but then you get to regions where you get to what's called semi-dilute. That was the first overlap, where they've started to bump into each other. The polymers have bumped into each other, but they haven't really changed shape, so they're not entangled. Then there's semi-dilute entangled, and that would be this one. And then you get into concentration not entangled, so that's this one. This is when the coils are now started to really squish together, and then they start to entangle. Now, why would I care? Why would I bother telling you this? And I don't think it's glaringly obvious just yet. But let's look at the Martin equation for a second. Now, this is by no means accurate in pretty much any of the regions other than dilute. But the viscosity of the mixture is exponentially related to the concentration. And remember, that's actually concentration times K times molecular weight raised to the A. So the the viscosity is roughly proportional to an exponential relationship for concentration and molecular weight. So as the molecular weight goes up, and as the concentration goes up, the viscosity of a polymer solution will exponentially rise at some point, particularly when the molecules start to entangle. Now, if I wanted to modify the viscosity of a product, and I wanted to do it preferably with not adding 50% of a material to do it, and I'd like to add a reasonably low concentration, but still get the viscosity up, that's exactly what a polymer can do. And it can do that because as soon as you start to get out of the dilute region, the polymers will start to bump into each other, and the moment they start to entangle, then you've really increased the viscosity in these systems very easily. And suddenly you go from polymer physics that seems a little abstract to how much material do I need to add to increase the viscosity in my product? Suddenly that becomes a much more useful conversation. And so we will get into the particle details of this next week. But in real systems, you've got if you put linear polymers in non-aqueous solvents, they're going to follow this type of macromolecule description. There's always something. Lovely. So in real systems, you're going to get polymers that kind of behave as spheres, particularly if you take synthetic polymers and put them in oils. They'll kind of behave like spheres in particle systems. And what happens is, although you can put polymers in aqueous systems and get that to work as well, is that polymers will act as thickeners and gelling agents. And I'm going to go into how that works from a rheological sense. We'll start with coagulated particle systems. But actually, as it turns out, there's a lot of industrial guides about thickeners and gelling agents, but not much literature on it. But it's very practical in terms of you want this type of polymer, you want it to not be toxic, you might want it about this size, and you can thicken or gel a system. Now, what we will talk about is what is the difference between thickening and gelling. We'll start with thickening. In thickeners, there's lots of examples, and what is annoying is what you'll find is the materials that gel and thicken are actually sometimes the same. So you can add agar, arrowroot, collagen, cornstarch, gelatin, guar gum, locust bean gum, pectin, tapioca, xanthan gum, all great thickeners. You might use them to thicken a sauce or a product to avoid sedimentation. You might, if you make the viscosity of the mixture thicker, particles settle slower too. When you make something thick, it has to not be stringy. The solution has to not be springy. It just has to be thick. So it still has to be creamy. Often what that means is that the polymers themselves actually need to be in rigid rod shapes. And because they help thicken this a solution without actually making it an elastic fluid or basically a gel. And so you can do this at low solids. Typically, these systems don't behave ideally. They're all rods, and they're about 10 weight percent. So you can't use those low viscosity descriptors anymore. But to thicken a solution, thickeners typically, you know, might find them in 5 to 10% as an additive, and they're adding as rods. Because they're rods, they bump into each other under flow. They're not, in thickeners, using thickeners, they might not be terribly entangled, maybe a little entangled, but it's more that they're rods and they might be able to orient and flow and increase the viscosity. And so thickeners are very common, and you could think of it in a sauce. Now let's talk about gels for a second. And you're going to talk about hydrogels in much more detail with Simone gives you a lecture. So we'll advertise polymer gels here. I'll talk about particle gels in flow next week, and then Simone will actually talk a lot more about particle hydrogels and their applications, which is really cool, by the way. But so gelling agents, you'll see alginate, agar, weight, carrageenan, locust bean gum, and xanthan gum, and pretty much all polysaccharides can be gelling agents. Now, and of course, gelatin, which is boiled collagen. So the differences in a gelling agent is could be a higher molecular weight, but in a gelling agent, the polymers don't just entangle, they cross-link. Sometimes they entangle and form physical cross-links, so you form a network of polymers. So the thickener might have been, if I had a flow of a pipe with a bunch of rods and it was a thickener and I was flowing it, all the rods might line up as they're moving along, and that's what those rods give me my increase in viscosity. But a gel, if I have a gel in a pipe, the individual polymers are going to be entangled and have cross-link points. I'm just trying to differentiate different chains. And in a gel, it's these cross-link or entanglement points that give it its increased viscosity. Now, those cross-link points can be mechanical overlap, or they can be chemical, like gelatin. So you can have a chemical cross-linked gel or a physically cross-linked one. Now, what happens is gels, because they have cross-link points, and the cross-link points cause the whole polymer network to drag when you try to put flow into it. Gels are springy. They can be much more elastic. Think of jelly for a second. They hold their shape much more, right? Think about icings. You see ice creams and frozen desserts. I'll ruin a food for you in a moment. But pharmaceuticals and cosmetics. And so one of the neat things about gels is because they form networks, strong gels, you don't have to add nearly as much of a material to get it to gel. You might only be around 2 weight percent of a polymer if you're adding a gel because it's cross-linked. And so it gets its increased viscosity, not because you've added a bunch of polymers, but you've added a small number of polymers that have all kind of networked together to be one large uber polymer that's much bigger. And you can see, and so as you can imagine, thickeners are great for manipulating sauces, but if you really want to try to manipulate flow properties of materials or a product, gels are amazing, particularly when you need that structure to it, like an icing. An icing is basically sugar and water. It doesn't flow because you put some cornstarch in it, and that's helped not just thicken it, but gel it as well. Frozen desserts, emulsifiers, I mean, cheap ice cream. Ice cream should melt. And when ice cream doesn't melt, and it's cheap ice cream, they've just put a lot of gelling agents in it to get it to gel. There are other ways where they try to impart structure. I think I've mentioned this, where you try to crystallize the fats into kind of a house of cards structure around bubbles. But really, cheap ice cream has emulsifiers in it, and they're polymers that form gels. Xanthan gum is just that. It's a gum, and it's used for cross-linking things as well. Alginate is an awesome gel. It's a great gelling agent. It's really useful. It doesn't have the temperature challenges that gelatin has, and it's vegetarian, so it's a really useful formulation product. It's just way more expensive than gelatin, where gelatin can be boiled from animal bones, either pig or beef. But gelling agents are very common in confectionaries, fillings as well. Gummy worms are a great example where they use gelatin. But that's actually, gummy worms are actually a really complicated system because they're about, I think, maybe 20% water in the end. What gummy worms are is gelatin, but they actually add a lot of starch. So they gel it, but they add starch. So they thicken it and gel it when they make a gummy worm. And so when you eat a gummy worm, it's not just sugar, it's not just fruit flavor, it's not just gelatin, it also ends up being like 45% starch as well. But the starch is kind of a thickener and then makes the whole system thick, where the gelatin is the part that cross-links it and makes it a gel. So gummy worms are very highly engineered. In fact, how they're made is freaky because they injection mold them in a starch mold. So the mold itself is made out of starch. They press a worm pattern into starch, and then they injection mold the liquid gummy worm into the starch. And why they use a starch mold is the starch is hygroscopic and it pulls water out of the gummy worm. Anyway, that's where I wanted to stop on polymers. When we come back to gelling and thickening, and in next week when we talk about rheology, we'll maybe even revisit this just for a second to talk about polymers again. But very practical. A lot of times to increase viscosity, you need to use a thickener, particularly shampoos. Things that you're going to pour, you want to thicken. Things that you want to stay springy and hold their shape, you want to make a gel out of. I don't care if that's a tissue engineering scaffold or a biological fluid that you want to flow, then you probably are looking more for a thickener than a gelling agent. All right. That's where we are on polymers. As I said, I think we're going to jump to emulsions. Sorry about this, just going back to the front, where polymers is one place where we've landed, but so that was our last big macromolecule. And what I want to do is try to finish up a discussion on particle suspensions. But don't worry, I'm not about to do stability ratio again. But I want to talk about, we've talked about basically hard particle suspensions, surfactants, and polymers. And we've talked about how surfactants and polymers might stick on suspensions. And you started to talk about emulsions a little with Amanda when you talked about HLB index. But I want to talk about emulsions in terms of all the things we've already covered in particle suspensions. We talked about particle formation. How do you make particles? Well, how do you make an emulsion? How are they stable? How do surface forces come into play? And then we're going to talk a little bit about how they flow, again, setting up for rheology for next week. But what's different about an emulsion is it's not like a dispersion in that it's soft. So hopefully you're going to come away with understanding there's different types of emulsions. You're going to see how they're formed. We'll talk about HLB index. I'm only going to skim over that because Amanda did such a great job, but I'm just trying to connect it to this a little bit more. We're going to talk about, but really I want to talk about how emulsions are made, what are the possible emulsions, and how do emulsions fail? Because they're more complicated than a particle dispersion, and they can fail in more ways than a particle dispersion might become unstable. And then hopefully we're going to just kind of connect to the particle dispersion stability work without actually having to do another stability calculation. And then we're going to talk about drop phase. So mixtures of two or more immiscible liquids, typically oil and water, are an emulsion. And you find them in foods. They're great for putting flavors. Cheese is an awesome emulsion, as is ice cream, although that's a triphase emulsion, a triphase system because it has solids in it. Salad dressing is a great example. In pharmaceuticals, we've got drops, we've got Scott's emulsion. Another great pharmaceutical is dipraverin, which is an anesthetic which knocks you out. It's called Dream Sleep. It's emulsified propofol, and then cosmetics. So many things are emulsions. They're either oil continuous systems where they have water in them, or they're water continuous and they have oil drops in them for moisturizers. And then lots of cleaning projects are emulsions as well, because the emulsion might hold the fragrance, or the emulsion might have a lot of surfactant in it as well. Fanta, I think, is technically an emulsion because those are flavor droplets of the citrus flavor in Fanta, or kind of finely dispersed emulsion drops, almost solids, to give you that flavor. So there's different types of emulsions, and it's defined on what the continuous system is. So a water-based system means that the water phase is the continuous phase, and the dispersed phase, which are the drops, is the oil phase. So a water-based system would be, there's a naming function, it's oil in water. So an OW is an oil emulsion, oil drops in water. An oil-based system is oil continuous, and then it's water drops in oil. And that's commonly referred to as a WO. So an OW is oil, an oil in water, and then a water in oil is water-based or oil-based. But the cool thing about emulsions is, unlike particles, you can put emulsions in emulsions. If you take, and this is going to sound funny, if you take a water in oil emulsion here, and then take that and emulsify it, where you add a small amount of that into a large amount of water, you can create what's called a double emulsion. And a double emulsion is just awesomeness, because then it's water in oil in water. So it's the little water drops in the oil in the big in the oil drops, which are then in water again. And so double emulsions, there's water in oil in water, which are WOWs, and then there's oil-based ones, which are OWs, oil and water and oil. Now, a double emulsion, so emulsions have a lot of different functions, because let's say I want to deliver a flavor that's soluble in the oil and not soluble in the water. Well, I could dissolve the flavor in the oil and then put it in the water, and I could deliver the flavor where I might taste the oil, but that's where the flavor is. The flavor is actually not in the water. And so emulsions are really good at protecting something, maybe a hydrophobic material in the oil phase, while it's a water continuous emulsion, and that's very common in drug delivery. But a double emulsion is even better. So let's say I've got a water-soluble flavor, but I don't want to use a lot of it. But it doesn't dissolve in an oil. So I can dissolve it in water, put it in a little bit of put it in oil drops, and then put it in a lot more water. And so when I go to eat that, as my tongue breaks up the little drops, I'll taste the flavor, but I didn't have to add that much flavor to get the taste, or I didn't have to add that much salt to get it to a taste for salt. So double emulsions can really help hide ingredients till you want to taste them or use them. That can also be used in single emulsions as well. So they can have much more useful formulation. They can be much more useful about incorporating materials in a formulation. But sometimes you might just be that you want to deliver oil drops, emollients to the skin. Maybe you want to deliver a moisturizer to a hair, and so you put oil drops, and nobody washes their hair in oil, but you might want to put conditioning drops in the oil, in water, and so you want to get the oil drops on your hair and to condition your hair, so you might emulsify that way as well. So emulsions have much more interesting abilities to deliver either the actual solvent or phase, as well as things you put in that phase for a product. It could be in a food, it could be in an oil, a cosmetic, and so there's a lot more flexibility in what you can use within an emulsion, and that's why you see them in product formulation so much. So how are emulsions made? And that comes down to, you've got oil and water, and they start off as separate phases. So you have to mix them. It requires energy. You have to mix the heck out of them. And after you make the drops in oil, or oil drops in water, or water drops in oil, you need to add something to prevent them from sticking together again, because they have a van der Waals force, and if you don't put a charge or a surfactant or a polymer in there to give a repulsion between the drops, they're going to separate again. So you have to add an emulsifier when you mix them up. Like their emulsions are used in a great many areas In fact, most of the world's explosives for mining are actually emulsions. They're amazing emulsions. I'll get to them in a second. How much energy you have to put into something to emulsify depends on how small you want the drops. The smaller it is, the bigger the energy cost. And on an industrial scale, the most common way to make an emulsion. Why does that keep happening? Is to shear it in a homogenizer. We'll try the cable instead. All right, we'll try the cable version. All right, so this is a cross section of a homogenizer. So you have emulsion drops that are pretty coarse. They're broken up, but not that much. And they're coming in this side. And what happens is they come in a flow field. There's some rotation there as well. But basically, you're taking those big drops, and this is rotating. And you're pushing them through a really tiny gap as you're rotating and creating a great large amount of shear. And as you push those oil drops through that small gap with all that shear, the oil drops deform and then break up. And that's actually how you get smaller drops. And sometimes you have to do this again and again. You then run the smaller drops in and you break them up and make them smaller and smaller. And so shear is actually how we make emulsions. And what happens, though, is they end up being quite polydisperse. So shear involves extending. If you have shear over a flat amount of oil, it's about extending the oil into fingers and breaking them up. But if you're breaking up a drop, really what you're breaking up is what's called a Rayleigh-Taylor instability. So instead of trying to think of shear is causing ripples on the surface of an oil and breaking them up, which can happen, let's think about a drop that we put in a flow field. And I'm going to say, I'm going to put it in a flow field. Sorry. Where I've got a complicated flow field. The shear's going that way on one part and it's going opposite in the other. And so what's going to happen to this drop is, instead of it being spherical, eventually it's going to elongate, and it elongates at an angle. But as a drop gets longer, let's say I have, the other thing I can do is an elongational. Well, the elongational shear is really what's in a homogenizer. So as I put a drop in, it gets extended. Sorry, let me draw an elongational flow field. I go through a nozzle. So I have a pipe that has a contraction. As the drop starts here, it's circular, but as it speeds up in this region, it gets pulled out to be a long drop. And as the drop gets longer, there's a force balance on the drop. And what's happening is, as the drop gets elongated, flow is pulling the drop. But there's an opposing force trying to get the drop back to a sphere. And that force is surface tension. So flow is pulling the drop and flattening it. But surface tension, or interfacial tension, is trying to restore the drop back to a sphere, because oil and water want to stay as a sphere because that minimizes their free energy. So the drop wants to remain as a sphere from thermodynamics, but flow is pulling it apart. And you have these two forces competing. The interfacial tension of the drop is trying to prevent it from breaking up, and it's trying to get it back to a sphere. But at some point, the flow will, if the contraction is designed right, the flow will work so that it will actually break up into two drops. And then as they move along, they'll kind of, as they come out of here, they'll end up being two drops. But they will actually, the drop will come along, it'll start to neck in the middle, and then, sorry, so it'll make more like a dumbbell shape as the drop starts to break up. And then it gets elongated, and then you're left with two drops that are spheres. And so this is this balance of flow, the flow applying shear on the drop and deforming it and flattening it and wanting to pull it apart, and the interfacial tension wanting to get back to a sphere. And this is called Rayleigh breakup. And why? And so Rayleigh breakup is great. It means if I put drops in shear, I can break big drops up into smaller drops, and I'll get two smaller drops. And that's awesome. But the problem is I'm going to end up with a polydisperse emulsion. Now, that might be good, that might be bad. And the reason is, let's say I've got one drop that's this size, one drop that's that size, and one drop, this is the same size. These two are the same size, and that's when it's bigger. When I break these up from Rayleigh breakup, I'm going to get two drops out of this where they're going to be about the same size, but they'll be smaller. I'll also get two drops out of this through Rayleigh breakup. They're going to be smaller. But when I break up this drop, I'm going to get two drops that are the same size, but they're both going to be bigger, and they're not the same size as these. And so then when these break up, I'm going to get two tinier drops. I'm going to get two tinier drops over here. When these guys break up, I'm going to get two tinier drops and two tinier drops here. The same is true for these two and for these two. And so now if I start to add up all the different sizes, what happens is if I make a histogram of the size, so drop size, when I break up drops with Rayleigh breakup, which is the common way it works in a homogenizer, I'll end up with a very broad distribution of drop sizes. So I'll have an average, but maybe if it's a good homogenizer, I might get it down to micron size or submicron. But I'll have an average drop size to it, but I won't really it'll be very polydisperse. Now, that can be good. As it turns out, if you're going to eat an emulsion, and you eat a monodisperse emulsion, it will taste gritty. And the reason is polydispersity is good. Your tongue, which is how you sense creaminess, is you take a food and you push it up against the roof of your mouth with your tongue. Now, you're all doing that at home right now. You're going, yeah, maybe. In an emulsion, when you do that, you're sensing the creaminess. And part of our creaminess texture is having all the little nooks and crannies in our tongue having filled up particles or droplets. So you can make something taste creamy just by making it polydisperse. So sometimes you want polydisperse to be great, but other times, if you're trying to control the release of something, or you're going to do a chemical reaction in an emulsion, you may want all the drops to be the same size. And so homogenizers, not a great way to get monodisperse emulsions. But there are ways to get monodisperse emulsions. And one of them is a cross-membrane flow, where you have say your oil phase, and you have a water phase. And what you do is you have a membrane where all the pores are the same size, and at the same rate, you push oil out of the membrane while you've got a parallel flow rate coming by and shearing the drops off. And by putting them all the drops out of this membrane at the same size, you can get a monodispersed system. And as long as you have some type of surfactant in solution to help stabilize the drops, they won't aggregate afterwards. You can do this in what's called a cross-flow membrane system, but the scalable one is called a rotating membrane system, where you have a bore where you're pushing the oil in, and this membrane is actually spinning around. And as it spins, that's where you get the even shear force that pulls off the drops as they come out of the membrane holes. We actually have one of these in our labs because we were doing a lot of emulsion projects where you're pushing, in this case, you're pushing water into oil, and then you're rotating this membrane and it's going around, and that's giving you that even shear, and you can make monodispersed emulsions. And you can vary the size of the emulsion just by varying the size of the membrane you're using. This is an example of an 8 micron emulsion we made that was very monodispersed. I mean, that isn't even the standard deviation. I think that's 2 standard deviations is like 2 microns each way. And this is a video microscopy image of our emulsion. Then we contrast enhanced it, and then we color coded it by size. And so you can see the diameter, regardless of how quickly we're making the emulsion, is pretty similar. And so you can make monodispersed emulsions. To get monodispersed emulsions really small takes a lot of energy, but technically getting any emulsion small. Below submicron in a homogenizer means you probably have to run it through several homogenizers to get this cascade of breaking up and generations of drops, which means to make emulsions, the smaller you want, the more expensive it is, because you have to get to higher and higher shear rates to break the drops smaller and smaller. All right. Let's talk about the challenge in emulsions. So, emulsions can flocculate, just like particle suspensions. We can not have repulsive forces, and they can flocculate. Now, when emulsions flocculate, they may go to the top. If you're doing an oil and water emulsion, oils are lighter than water. So emulsions cream sometimes. It's called creaming, obviously, because milk creams, but that's when the drops are lighter than the continuous phase. If they're heavier than the continuous phase, they sediment. But the things that you'd expect to happen from particles, they can fail from buoyancy, they might sediment, or in this case, cream, or they could flocculate if you don't have very good surface force control. Now, flocculation is when the drops get stuck together, but maybe they have coatings on them, so they're still drops, individual drops, but they're stuck together, kind of looking like particles stuck together. Drops also have the great, fantastic ability to coalesce, which means if they don't have a very thick coating on them or there isn't a lot of surfactant, when they stick together, they'll stick together as just bigger and bigger drops. And in fact, drops can coalesce very often into completely separated phases, and that's what might be what happens when you shake up salad dressing. Over time, you'll see the oil and the water separate. So emulsions have other ways to fail other than what you'd think for particle dispersions. What's great is emulsions have many ways to fail. One of my favorite is phase inversion. Phase inversion is literally just what it says. This happens an awful lot when you have emulsions that are kind of 50-50 continuous and dispersed phase, is that 1 minute it's oil continuous and the next minute it's water continuous. And if that is not the product you were hoping to make, where you've put a lot of oil in a water system and somebody thinks, oh, it's going to be watery, and then it phase inverts and it turns oily, that could be a problem. So we'll talk a little bit about phase inversion in the context of HLB. Phase inversion, a lot of times in formulation, is set off by changes in temperature. So you might have, it might be stable at one temperature, but let's say it heats up and the stabilizers change and suddenly it phase inverts. By the way, it doesn't have to be 50-50. You can have a continuous phase emulsion. I'll draw one out and I'll show you a few later. If I had a cross-section of a bunch of drops and they were packed together very, very closely, I could have a continuous phase emulsion where the volume fraction of the continuous phase, I don't know, could be like 8 to 10%, and the volume fraction of the dispersed phase could be like 80%. So you can actually have very high dispersed phases. And in fact, emulsion explosives are something like 80% aqueous phase, but it's dispersed. So they're only, I think, 8 to 20% continuous phase. And so you can have a high internal phase emulsion. So, and those can phase invert as well. By the way, you might make an emulsion like this where it has a very high dispersed phase because you want a very high rheology. You might want to make it very viscous or control its flow properties. So you might make it a very high, have a large number of drops in a very high dispersed phase. So phase inversion is a problem. The other thing emulsions can do is Oswald ripen. So Oswald ripening is not your drops didn't work out because they coalesced. They dissolved. And why they dissolved was simply because they were small. That's a pretty freaky reason to have drops dissolve. And we'll get to that in a moment. So I was going to write a bit more here, but I just kind of wanted to go through the different, excuse me for one sec as I open up my notes, on this computer. The different, talk a little bit more in detail about the different ways emulsions fail, and then we'll talk about how they're used in a little bit more. So if you start with a 50-50 volume oil-water emulsion, which phase is going to be continuous? Which phase is going to be dispersed? Because you can have either outcome. And a lot of times what controls that is the stabilizer you choose, not just for 50-50 mixtures, particularly if you've chosen a stabilizer that's going to make it oil and water, and you started out as water and oil, and it can invert. And so you've already had a discussion about HLB. This is just a reminder that different surfactants are weighted better to work as water and oil emulsifiers or oil and water. And you can look up their HLB indexes or Griffith indexes, where water and oil emulsifiers, so water drops and oil, are kind of lower, oil and water are higher. Now, really high HLBs are things like detergents and solubilizers, and then you've got wetting agents in there as well. But kind of the 4 to 6 range, or the 8 to 18 are sweet. And so if you want a oil continuous emulsion and you use a water continuous emulsifier, that's when you're setting yourself up for possibilities of phase inversion. You guys have already gone through HLB index, so I don't want to do that again other than to just kind of give you that range. But in designing an HLB, you have to ask yourself, do you want it to be oil and water or water and oil? And that will really matter what emulsifier you pick. And if you pick the wrong one, but you go, no, I did get it as water and oil, but I used an oil-water emulsifier. You did it when you started, but I guarantee a bump in the road, a little bit of energy near that emulsion, and it'll phase invert. Other things decide your HLB specifications, or what looks good in an emulsifier is how long do you need it to stay stable? How much does it cost? Typically in an emulsion formulation, the most expensive thing is the surfactant. Is your emulsifier going to be stable towards salts? If it's ionic, it is going to work less effectively if you add salt in it. Is it going to decay over time? Is it going to oxidize? A lot of surfactants have to be non-toxic or non-irritating. And remember, surfactants are good, particularly detergents and solubilizers are good at detergent and solubilizing skin. They can pull oils out of your skin. They can pull fatty acids out of your skin. In fact, one of the reasons soap is full of moisturizers, right? Soap, Dove soap, solid bar soap isn't just soap. Soap is just surfactants. What is in a bar of soap is surfactants and fatty acids. And the reason is the fatty acids are in your skin and go between your skin cells. And so when you have like Dove, it's 1/4 moisturizer, is really about that when you use soap on your skin, you're trying not to dissolve those fatty acids, and you're actually trying to put fatty acids back into your skin because the surfactant peeled some of them off. And so you don't want surfactants to be irritating, and they can. Shaving creams and shaving gels are another great example where people used to shave with soap, but that actually would dry out people's skin because the soap wouldn't just lubricate the razor, it would solubilize all the fatty acids in between your skin cells, and it would make your skin dry. And so a lot of the shaving gels now are designed with soaps that are designed to maybe not solubilize that as much, but they're higher molecular weight, so they're almost polymeric, so they provide lubrication in friction, but they actually add fatty acids, or they'll add things that are called humectants, which are molecules that are designed to hold water and keep that water on your skin to moisturize. One of the jokes about the key ingredient in a moisturizer is not the oil continuous phase, the polyethylene glycol, that all the different additives that make you spread a moisturizer. The secret ingredient in moisturizers is water. And so a moisturizer is designed to deliver water drops to your skin and keep them there to keep your skin moist. Everything else there is just about delivering water. A moisturizer, most of the time, is a little bit of polymer, but the secret ingredient in moisturizers is water. Now, and also when you're looking at surfactant, you have to think about how you manufacture your equipment, how it's supplied, and that'll affect your choice of emulsifier as well. But I didn't want to spend too much time on HLB stuff. This is a reference I will what you can find is if you're starting to look at surfactants, particularly when you start to look at the products you're engineering, you'll find that there's a lot of commercial names for surfactants, and you kind of need to look them up to see what on earth it actually is. Now, this is a notebook, this is a reference book, and so there's lots of older references, but now you just have the internet and you can look them up. But you really do need to look at your emulsifiers and your polymers if you're looking at formulations in your products, and actually look up what those materials are, find out whether or not they're amphiphilic, or they're surfactant, or they ionic, or they zwitterionic, what's their HLP index, are they polymers, are they block copolymers, what's their molecular weights, are they water-soluble polymers, are they oil-soluble polymers? These are really things that you're going to need to start looking up when you look at your polymers or surfactants. Now, so poor surfactant choice will often lead to phase inversion. Let's talk about Oswald ripening. Why on earth? Emulsions can dissolve. So can foams. And the reason why is not what you think. Well, because if I take an oil is not really soluble in, most oils are not soluble in water. If I take an alkane, it's not like octane, decane. It's not really soluble in water. It's sparingly, tinily soluble in water. But if I make a emulsion out of octane drops in water, it may actually dissolve over time and separate. And the process is called Oswald ripening. But the reason behind it is because drops have something called the Laplace pressure. And this isn't true in particles. So I don't care if I have a drop or bubble. In each case, well, bubbles, of course, we have an inner and an outer, right? We have two layers. We have a film of, a bubble is two layers of two films with water in between. That's what makes up a bubble. And so there's a force, there's a tension, because water has a surface tension, and so does oil drops. And so the easiest way to think of what is surface tension is have a glass. If we have a glass and then we fill it up with water, we start filling up our glass with water. We start filling up our glass with water. And then right at the top, right, I'm just going to draw the top of the glass. Have you ever noticed that when you fill up a glass with water and it starts to get, and you've filled it up, that what happens is the glass, the water, goes above the lip of the glass, and you still see a little bit of water over there. And then if you add one more drop, so you add one more drop to here, and then it flows over. And so before that water overflows the glass, there's a tension. And the water is kind of holding back, and it's actually holding back the weight of the water a little bit, and it's not overflowing in the glass. And that's because the surface of water has a tension to it. And that surface tension arises from the fact that the water molecules would much rather prefer to be around other water molecules than air. And so energetically, it forms kind of a layer of organized water molecules on the surface that leads to a tension. And so surface tension, when you take a small object like a bubble, if you do a force balance on this, there's the pressure pushing in on the bubble, but there's also a pressure pushing out. So there's a pressure pushing in, and there's a pressure from the inside, and there's a pressure from the outside. And what happens is this outward force, which is the pressure pushing out from inside the bubble, and the inward force, pressure pushing in outside from pushing out from inside the bubble. When you do a force balance on these two things, what you find is that the pressure inside the bubble or inside a drop, because of the mismatch in the radius and the mismatch in the pressure, there's actually a pressure difference from the fact that the drop is curved. Now, without taking that on face and just deciding that Laplace was pretty smart, Laplace figured out that the pressure on the inside of a bubble compared to the outside, that the pressure is higher on the inside, and it's proportional to 2 times the surface tension divided by the radius. And so if the radius is big, that really doesn't matter. But if it's small, it does. And so, by the way, Laplace figured this out while looking at modeling celestial bodies. It's actually in an appendix there where he pointed out, oh, curved surfaces have a higher pressure on the inside than on the outside, just from the fact that they're curved. And that surface tension or interfacial tension is pulling in on those molecules, and it creates a slightly higher pressure from that surface tension. And that increases the pressure inside a drop or a bubble. Now, you can use the Laplace equation to calculate the pressure difference inside. I've got a droplet of tetradecane where I know the interfacial tension is 52, and I've got a droplet of water. I've got a bubble where the interfacial tension is 72, surface tension. Now, what I'd like you to do is use the 2 gamma on R, knowing that 72 millinewtons per meter is 0.072 newtons per meter. And the same you'll need to do for that. And remember, that's 1 times 10 to the minus 3. That's 1 times 10 to the minus 6. That's 100 times 10 to the minus 9. And that's 1 times 10 to the minus 9. What I would like you guys to do is actually go calculate the Laplace pressure, because I'm going to ask you to do it on an exam at some point. So I'll give you something to pause the video on. Oh, awesome. You guys are going to love this. So, this is a reproduction of the original from when I was a kid. This is a great thing to pause the video on. Let me make sure it's in the capture part. This is Voltron, of course, the 5-lion Voltron. The 5 lions form 1 large lion. This is the original Voltron toy. So pause it on Defender of the Universe while you do your calculation. Okay, so I hope you enjoyed Voltron in your background while you were doing this calculation. Now, you were supposed to do the calculation in pascals, and I'm just going to write in 1. I'll write in the water 1. So for a bubble, it's what? 104.00. So that's how many pascals. So that's basically 1.42 atmospheres. But the thing is, as we get smaller, it gets disturbingly large. I mean, at a micron, you're at 1421 atmospheres. And then it just gets stupid after that. By the time you get down here, it's 1.42, 1, 2, 3, 4, 5, 6 times 10 to the 6 atmospheres of pressure inside the bubble. So in a millimeter bubble, who cares? But in a millimeter, that's a very small pressure. It's not that big of a pressure. But can I divide that by 101.325? Yeah. My calculation is off by 1,000. Sorry. That's better. I did my unit calculation wrong. Let me just erase those. All right, so this makes more sense. It's 144 pascals at 1 millimeter. So the pressure difference there is tiny. But, you know, at a micron, it's 1.42 atmospheres. And it's 1,400 atmospheres at a nanometer. And so what that makes us wonder is what happens to an oil when it's at a much higher pressure? What happens to a gas when it's at a much higher pressure than it would be in the bulk? Well, it affects its solubility. Actually, technically what it affects is its chemical potential. So when the insides of these drops are bubbles that are much higher pressures, they're at much higher chemical potentials, and it also means they're at much higher solubilities. And so these higher pressures mean oils that wouldn't normally dissolve in a big drop will dissolve in a small one. And if you have a population of big drops and small drops and big drops and other small drops, the pressure difference of this small drop is much larger than the pressure difference of the big drop. And so what happens with these drops with the smaller pressure, or the smaller drops with the higher pressure, is those drops dissolve And the oil from those drops will then be driven into the water and deposit on the bigger drops. And so if you have a polydispersed population of drops, of emulsion drops, say oil drops in water, the small drops will dissolve because of their higher Laplace pressure, and the oil will then deposit into the larger drops. So the larger drops grow at the cost of the smaller drops. And that is called Oswald ripening. And it's driven by the Laplace pressure. But if you make a polydisperse emulsion, over time, it will destabilize from Oswald ripening. So it's cheaper to make a polydisperse emulsion, and you might want that, but you might want the emulsion to stay polydisperse until it's used. And so then the challenge is you have to put surfactant coatings in, or sometimes there's tricks where you can use mixtures of oils. You add a little bit of a very heavyweight molecular oil into a system that's a lighter weight molecular oil, just to try to control the Oswald ripening effects. So Oswald ripening is this other way for emulsions to fail. Quite frustrating, by the way. Sometimes if you want to study the effect of, say, a stabilizer on the stability of an emulsion, you need an emulsion where it isn't affected by Oswald ripening. So you might study a model emulsion as a monodisperse emulsion, figure out what stabilizer and what concentration is useful to keep the drop stable from colloidal forces, and then try to make the same system polydisperse and see if it's stable against Oswald ripening. So emulsions offer a lot more pathways to fail, to become unstable, and you have to think about engineering for all of those cases. So when you think of a particle size distribution, oh, it's a particle, it's solid. But when you think about drops, you have to worry about Oswald ripening. Now, Oswald ripening happens anytime you have particles or drops with an enhanced solubility. But when you have particles that are surprisingly have an appreciable solubility in their continuous solvent, and they're very small particles, it's called the Kelvin effect then, not Oswald ripening, but it's similar thermodynamics where you can have the particles change in size, particularly if it's a solid particle that's reasonably soluble in the solvent it's suspended in. This is very common in agrochemical powders, where you'll actually see the particle size distribution drift from Oswald ripening in a solid that's actually reasonably soluble in its dispersed phase, a continuous phase. All right. Now, oil drops. Do they have surface forces? Does an oil drop have a surface force to it? How do you study colloidal forces when you have oil drops? And as it turns out, emulsion stability is analogous to DLVO theory. You can have charged surfaces and have electrical double layer forces. You can have a van der Waals force, and you can add them together. And I'm going to mention a little bit of this where you do not have to know the great details of how this was measured, but we've used a measurement technique. We're going to talk about atomic force microscopy in the characterization method later in the semester. But here I'm just talking about how we've used it to do collisions between microdrops in lab. And my lab actually invented this method to collide or drive two oil drops. One is immobilized on the bottom surface, and the top is immobilized on what's called an atomic force microscope cantilever, which is really just a thin piece of metal that behaves like a spring. And underwater, we stuck an oil drop underneath it, and we stuck another one on the surface. And then the top cantilever is a very sensitive spring, so it measures the force between the two drops very accurately. People often say, well, how do you get an oil drop in an AFM? Because these drops are about 40 microns in radius, so they're about the same size as the thickness of your hair. And what we do is we generate a population of bubbles or drops on a surface. We use our AFM like a micro manipulator, and we'll pick up a bubble or a drop, and then we'll move it over another bubble, and then we'll just bring it down in just the Z direction and measure how much this cantilever bends, or the forces between the two bubbles. And to do this, we of course, we actually, it took a lot of work. We actually make our own AFM micro cantilevers. They're made out of silicone, and they have a cute little circular patch on them that we chemically modify, and that keeps the dropper bubble in place. And so we make these cantilevers, and actually we make them at the Melbourne Center for Nanofabrication. All of my PhD students know how to do nanofabrication now. They use CVD deposition, E-beam deposition. They use deep reactive ion etching and photolithography to be able to make these micro cantilevers. This is a cool picture. Our AFM, our atomic force microscope, is mounted on an inverted microscope, and we used it like a periscope. So this is actually what the AFM measurement looks like from the side through a microscope. And so those are two bubbles, and we're about to squeeze them together very thin, so the separation between the bubbles easily gets down to a couple nanometers, just like it would, just as it's relevant for those force laws. And we're able to squeeze those two drops together and understand what the forces are at play between two bubbles or two drops. Just as an example, I'm gonna show you one example where we measured the surface charge of bubbles. So we made bubbles out of different gases. So we blew micro bubbles of different gases, and we looked at changing the pH. So we didn't have any surfactant there. It was just air bubbles in water. And so we took air bubbles and we squeezed them together. And at low pHs, you see an attractive force, which is from van der Waals. At higher pHs, you start to see a repulsive force and then an attractive force. And then at really high pHs, you see just a repulsive force as we squeeze the two bubbles together. And so that's an electrical double layer force. This is an electrical double layer and van der Waals force. And then at pH 4, we're just getting a van der Waals force. There's a model, which I'm probably not going to go in. Because the drops or bubbles squish and deform as you squeeze them together, the analysis steps are a fair bit more complicated. But what we're able to do from that is, instead of just going, oh, look, the bubbles didn't stick together, oh, look, here the bubbles coalesced, we use that model to actually pull out surface potential. So I mentioned in the particle dispersion discussions, you can measure the charge, the surface charge on a particle and its potential, and we called that the zeta potential, and said that was about equal to the surface potential. Well, with AFM, you can directly measure the surface potential, and we've done that for bubbles. And so this is the surface potential that we measured in our AFM as a function of pH. And at pH 10, the bubbles didn't coalesce, and we measured a surface potential of around a minus 100. But maybe between pHs of around 4 to 6 or 4 to 7, the bubbles did coalesce, and the surface potentials went down. And in fact, at just below pH 4, just around pH 4, the surface potential went to 0, because the charging there is from an effect of pH. And so we could actually measure the surface potential between two bubbles just by squeezing them together. And what we did was we took this force versus basically separation law and compared it to an electrical double layer, DLVO, model, and we're able to fit or extract out the surface potential. So the same models I was showing you to predict stability, we actually were using to measure the surface charge of bubbles, and then from that we could talk about bubble stability. Now, we did this for air, and we wanted to make sure our method worked, and there is actually some electrokinetic data where they made bubbles in a column and then applied an electric field and measured their electrophoretic mobility, very similar to the formulas I'd given you in particle dispersions, but they've done it for bubbles. And so while their negative is going up and our negative is going down, we got about the same zero charge point and similar values for our data and theirs. So that was nice. But we did it with air, but then we did it with argon and nitrogen as well. And something that's interesting is the surface charge of an air bubble and the surface charge. So argon and nitrogen have almost the same surface charge or surface potential. Regardless if you have argon or nitrogen, they have the same charge. But air's charge or air's surface potential is different. And so air, which is mostly nitrogen, by the way, and some oxygen and a little bit of argon, has a very different surface potential than nitrogen on its own or argon on its own. And the difference is actually because of carbon dioxide. Carbon dioxide as a gas is surface active. So the surface tension of water and air is 72 millinewtons per meter. But the surface tension of water with carbon dioxide is 65 millinewtons per meter. So carbon dioxide, because it reacts and forms carbonic acid, is actually surface active. And so the carbon dioxide in the air enriches at the bubble interface, and it affects the actual surface potential of the bubbles, even though there's about 390 ppm of carbon dioxide in air. So it's 0.039%, but it affects the surface charge of bubbles just because carbon dioxide is surface active. So you get a different surface potential for an air bubble compared to a nitrogen bubble. You can also look at the surface charge between oil drops. These are fluorinated octane oil drops. And similar things, you can change the pH. And in fact, oil drops have very similar surface potentials, and they're actually similar to argon and nitrogen. But air does kind of stand out as its own type of surface charge because of carbon dioxide. And so this was kind of interesting, and this shows you that I'm showing you an example with just gas bubbles or liquid drops, but we put polymers here and surfactants and look at those forces for formulated products as well. We've done a lot of work with AFM looking at the stability of emulsions and shampoos and processed foods, figuring out what stabilizers are useful at providing repulsive forces when we go to formulate an emulsion. So we used this same AFM method as a product development tool to screen different types of surfactants. I'm going to skip over that. One, it didn't reproduce well. I don't know what happened here. But the details here, we can try. This is the pressure between two drops. This would be the DLVO model that's similar to the ones you've already calculated. And you can see there's a Vmax or a Pmax, which would correspond to a Vmax. And that was what would you use for stability ratio. But if the drops are big enough, their Laplace pressure will intersect with that DLVO curve. And I guess that what I'm really talking about here is that when the drops deform, at some point, if the pressure between the drops from the surface forces causes the drops to deform and flatten, they won't actually get closer together. So if I have two drops, and if I have two particles and I drive them together, I keep pushing them together, they're going to stick. But if I have two drops and I push them together, if the surface forces cause the drops to flatten, no matter how much I push, they won't actually get closer together in the center. They'll just flatten. They'll get bigger radially, but they won't actually connect. And on what that translates to quantitatively is when the Laplace pressure is less than Pmax, the drops actually flatten and won't coalesce. The Laplace pressure has to be higher than Pmax, and a high Laplace pressure means small drops might coalesce, but big drops won't because they're floppy and they deform and they won't get close enough together. So if your repulsive force, if your Pmax or your maximum repulsive force is greater than your Laplace pressure, these drops won't coalesce. Now, the details of that will seem odd. Don't feel freaked out about that, but particles don't have a Laplace pressure. They don't deform. So simply because the drops deform, the surface forces between the two drops could actually cause the drops to flatten and prevent them from coming into contact. So drops can stay stable often with surface forces that particles couldn't. This is just a comment that if you're curious, I am happy to talk to you a lot about different ways you can look at the interactions between drops. We're working in microfluidic channels now, trying to connect what we do in an AFM to a microfluidic device. We've looked at what happens when you add lots of surfactant and lots of polymers between drops. We've also looked at what happens when you have flow between drops as you look at collisions. And because we're good at squashing soft things with AFMs, we've also looked at the mechanical strength and nanomechanics of capsules that are used in drug delivery, milk fat globules that are in dairy milk, as well as capsules that are used in food processing for adding flavors and things. So we've worked a lot in that space. The final two things I want to talk about are emulsion flow. I already introduced the Stokes-Einstein expression for a polymer. As I said, this is really just a way to describe how the viscosity in low concentrations of added solids increases. So you take the solvent viscosity and the volume fraction of the material, assuming it's spheres, and you can predict what the mixture viscosity is going to be. And this is the Einstein relationship. Now, if I had just particles, Einstein would hold really well. Emulsion drops are more interesting from a fluid mechanics standpoint. And the reason is, if I don't have any surfactants, if I have an emulsion drop move, as the emulsion drop moves, it drags liquid motion on the surface. So when emulsion drops move in water, they get in a surface flow, which then connects to an internal flow, and drops actually have a recirculation pattern in them as they move. And this is because there's a continuity and momentum across this interface. Chemical engineers can think of it as pipe flow, where if you had water and oil flowing in a pipe, the velocity profile would be continuous at the point where the oil and water connect. But what happens is, because the drop interface can have a surface flow and it can have motion, when drops move around, they actually can have an additional flow to them. This can sometimes be called it's just a recirculative flow, but it can also be called a Marangoni flow, and I'll show you a cool example of that in real life for important parts of life in just a moment. But whether or not you have to worry about flow depends on the viscosity of the solvent and the drop. And so instead of 2.5, you actually have to put in this K factor, which is 2.5 times this ratio of viscosities, where drop flow is a little bit more complicated because you can get this internal circulation. And so this is just another way drops are more interesting. It means if you have a particle suspension at a particular volume fraction, and then you have an emulsion at the same volume fraction, the emulsion could actually have a lower viscosity, even though it's the same volume fraction, just from the fact that you get internal circulation in the drops. So emulsions are more interesting than rigid surfaces. This is the Einstein version, which is for very low concentrations. You can get up to about 5% using, this is basically an additional higher order series correction to Einstein's approximation, and it's called the Krieger-Doherty expression, which we'll come back to for rheology. What's different about Krieger-Doherty is it has this B and C in it, and those account for the fact that you're getting now to the point where the drops or particles would interact with each other. So there's additional parameters to characterize particle interactions that are neglected in the Einstein relationship. But these are ways to talk about suspension flow with very simple predictions, perhaps without having to measure things in detail. Now, another cool thing about emulsions is how they pack. So these are actually monodispersed emulsion drops we generated in a microfluidic device in our lab. And you can see that they're monodispersed. Hard spheres this is the highest packing they'll get. It's about 64% is their effective high packing for monodispersed spheres. And so the void spaces, you can't get any more better than that. And this is just a multi-layer effect. But emulsions, because the drops can deform, you can cram more drops in. And when you do that, you go from basically packing of spheres to effectively packing of hexagons, where this might be the dispersed phase, and the continuous phase is kind of this hexagonal matrix that's in 3 dimensions. And so for soft materials, you can actually get to much higher effective packing fractions as well. And so the highest packing fraction you can get for monodispersed spheres is 64%, but you can get to much higher ones. And so I mentioned emulsion explosives, which have packing fractions that their effective volume fractions are around 80 to, I think, 85% dispersed phase. And so these are emulsion explosives. And emulsion explosives are basically ammonium nitrate drops full of ammonium nitrate emulsified in diesel oil. And what makes this possible is a very well-engineered stabilizer that's designed with an appropriate HLB index so that it does not phase invert. So it's a high internal phase emulsion. By the way, that's high internal phase emulsion, or HYPE, is just when you have a lot of the dispersed phase in a very small volume fraction of continuous phase. But high internal phase emulsion explosives are exceptionally safe. They can be stored in silos. They're pumped around. They have amazing flow properties. They basically are very thick. They're thixotropic, which means you can flow. They'll kind of hold their shape. And the reason why is, does anybody know how emulsion explosives are actually used in practice? So in a mine, when they drill, for a rock face, they bore underneath the rock in an open pit mine, and then they drill holes up into the rock, several meters, and maybe even 10 meters. And then, so they have all these holes that are facing down into an open bore cut. And so then they pump the emulsion up these boreholes. The explosive emulsion goes up and then has to stay in the boreholes for a couple days before they finish filling everything and then putting all the detonators in, and then detonate it and explode, and the emulsion falls down. So this emulsion has to be able to mix, it has to be able to flow in pipes, but then when it stops flowing, it has to stay in these boreholes against gravity. And so it's quite a remarkable emulsion in its flow properties, and a lot of it comes from the fact that it's a very engineered high internal phase emulsion. So it's added a lot of drops to give it a very high viscosity, and then the stabilizer itself also contributes to its flow properties as well. So emulsions can be really amazing materials for flow properties. So I think this has been a long lecture, and so I want to finish with something that you can do as homework, and it's a life skill too. So I'm gonna. I think the camera's on now. So I want to talk about Marangoni flow. So we said drops can have an internal circulation, but you can guess who this is named after. Marangoni had identified that you can get what's called a surface tension driven flow. And the example we have is, if you've ever watched someone drink a glass of wine or drank a glass of wine, this works better with red wine, not just because red wine tastes better, but because you can see it easier. If you swirl a glass of wine, what you'll see is after you swirl it, after a little bit amount of time, you'll see these teardrops of wine kind of drop back down into the glass. And that's actually the result of a rather complex fluid mechanics problem. And so what happens is when you swirl that glass, you get a very high, you've increased the surface area, and you have this film of liquid. And at the top of that liquid, the ethanol evaporates. In fact, at the top of that liquid, where it's actually a little warmer, that ethanol, initially a little bit warmer and it's thinner, the ethanol evaporates out of the wine. Now, when the ethanol evaporates, what happens when a liquid evaporates out of a mixture? It cools down. So when the ethanol evaporates, it cools down the liquid at this end. And when you cool down the liquid, surface tension is a function of temperature. So surface tension versus temperature actually is an inverse function of temperature. So as the temperature goes down, the surface tension goes up. So as that ethanol evaporates and cools down this upper rim of the film, the surface tension suddenly gets higher at the end of the film than it is further down in the wine glass. So that higher surface tension pulls the liquid up along the surface of that glass. So if I draw the side of the glass, and I've got this thin film of water that then goes out, the surface tension actually pulls liquid up this film around to the top, and I get extra amounts of water piling up at the top of this film. And eventually that water gets so that you get so much liquid at the top that gravity then makes it come back down. And so you get these teardrops in the glass that fall back down. Now, I said this could be a life skill. The Marangoni effect requires you have to have enough ethanol in the wine so that it'll evaporate enough to cool down the wine enough to change the surface tension. And I believe you need about 4% wine or better. 4% alcohol in the solution. So if you ever order a house wine and swirl it, and you don't see the teardrops form, they've watered down the house wine and you should send it back. And I have actually had a colleague who was a chemist who sent a house wine back at an Italian restaurant in Italy on the argument that when he swirled the glass, it did not make the teardrops, and he said he accused the restaurant of watering down the wine. And I don't think he spoke Italian, so it was a bit interesting on its own. But so it's a good life skill, and it's a great example of a fluid mechanics problem. So I think we're gonna stop it there, and I'm hoping in the consultation on Thursday that I'll talk about Marangoni flows, and we'll talk about emulsions and viscosity and maybe some more interesting product stories, as well as field your questions. So thanks.